All right, hello everyone. Welcome to an in-person APS colloquium. Yay. And I'm going to introduce today's speaker, who is Melodie Kao, currently at the University of California, Santa Cruz. So Melodie is an expert in radio observations of brown dwarfs and using those radio observations to learn about aurora happening on bodies elsewhere in our galaxy and learning about the magnetospheres of these objects, using those radio observations to figure out what we can learn. So Melodie was an undergrad, hold on, let me get this straight. Melodie was an undergrad at MIT who graduated in 2011 with degrees in physics and a concentration in architecture, because that's the traditional pairing with physics, it turns out. And then after that, graduated from Caltech in 2017 with a PhD in astrophysics. You've done postdoc, you were a postdoc and Hubble Fellow at Arizona State University following your PhD. And then in October of this year, moved to, at Arizona State, she was a postdoc with Evgenia Shkolnik, who we've had here to give a colloquium in the past. And then as of October of this year, she moved to UC Santa Cruz as a Heisig-Simons 51 Peg B Fellow, supervised by Jonathan Fortney, or paired with Jonathan Fortney at Santa Cruz. I think that's it, other than here's Melodie, something like that. Okay.
Okay, sounds good. All right, so thank you, Dave, for the introduction. And just in general, I'm super jazzed to be here and in person. I've been following a lot of the research coming out of this community for several years now. You'll see from later in this talk that I draw a lot of inspiration from the planetary folks here. And I'm hoping that I'll be able to come back regularly over the next several years because I have some close collaborators in this community. Okay, so as Dave said, I study magnetism in brown dwarfs so that we can learn about magnetism in gas giant exoplanets. And just can I have a show of hands who here is familiar with what brown dwarfs are? Because I know I'm talking with a broad community of people. Okay, great. So ultimately, the big picture question that I'm interested in is how does magnetism impact exoplanet systems? Now, I think that magnetism or magnetic fields are fascinating to study because they are a fundamental property of planets. And we know that magnetic interactions with local environments, for instance, can influence the planetary atmospheres and also the evolution of their angular momenta. And also the properties of their magnetic fields probe their deep interior physics. But to really answer this big picture question, how does magnetism impact exoplanet systems? We really are at the point right now where we have to go back to basics and first understand their magnetic behaviors and what their magnetism can tell us about what else is going on. And so that's really what I focus on in my own research. So to elaborate more on why characterizing planetary magnetism is just so critical to understanding their evolution, I always like to start with this incredibly beautiful image of the sun's corona during the 2017 total solar eclipse. And if you were listening to Dave's introduction closely, you'll note that this was the summer that I was finishing my PhD. So I heard there was a large contingent of CU folks who went out and saw the eclipse, but I was stuck in an office finishing my thesis. Nevertheless, I really enjoyed the images that came out. And what we see here is that you can see kind of this bump over here. And this is a solar prominence, which one can think of as dense plasma that's flowing along one of the sun's tangled and twisting magnetic field lines. And so since their birth, the planets in our solar system have been interacting with the sun's magnetic activity and solar wind, as well as the radiation environment from the sun, including its UV radiation, which Kevin Franz and Sebastian Pineda work on characterizing and sort of the implications of that on planetary atmospheres. So when something like a prominence becomes unstable, for instance, it can violently, eject hot ionized gas and magnetic fields. that can then sort of run into a planet and in some cases carry away some of its atmosphere. So during a solar storm, for instance, the flux of oxygen ions escaping from Earth increases by a factor of about 10 times. When we look at Mars's relative atmospheric loss response to the same solar storm, there's actually a factor of 10 times more atmospheric outflow. So over 4.5 billion years, the remaining atmosphere on Mars seems to have been enriched with heavy isotopes relative to Earth's. And unlike Earth, the engine that's sustaining Mars's magnetic field shut off pretty early in its lifetime, about 4 billion years ago, leaving only this remnant field that's frozen into its crust and then no strong global magnetic field. And Dave Brain had some really lovely work in 2017 that showed that when Mars's stronger crustal fields are on the day side, so facing the sun, it experiences less atmospheric escape than when its less magnetized side rotates into the sun's view. Right? So, I've been following Dave's work closely for several years, and one thing that I appreciate that he always says in his public talks is that how magnetic fields influence atmospheric evolution is still very much open to debate. And there's this really cool center now, the Mach Center based here, that will be looking at exactly this question. But we can say that planetary magnetic fields do appear to modulate atmospheric evaporation somehow in a very complex interaction, right? Okay, so more recent observations from the exoplanet side of the community is showing that magnetic fields seem to also influence planetary angular momentum evolution. So recent observations by Marta Bryan, who is a 51 Peg Fellow, or was a 51 Peg Fellow, now a Sagan Fellow at UC Berkeley, suggest that magnetic coupling with circumplanetary disks can cause young planets to rapidly spin down and quickly lose their angular momentum. And then similarly, magnetic torquing can actually potentially explain some of her measurements of misaligned planetary spin axes with respect to their host stars. And this is a very recent development. The theory is still nascent, but it's one of the leading theories is that it's some kind of a magnetic interaction. Okay, and then finally, back to where I first started in graduate school, since their deep interior fluid flows, for instance, from rotation and convection together with the Lorentz force, are actually what work together to act as a dynamo mechanism to generate or to induce magnetic fields in planets. These magnetic fields and their properties also serve as the only direct probes into planetary or interior dynamics and properties. These properties might include conductivity, viscosity, density stratification, and these properties in turn influence things like the field strengths, their shapes, and their time varying behavior. And so as an example, in 2018, a team that was led by then grad student and now 51 Peg B Fellow Kimmy Moore mapped Jupiter's magnetic field using Juno magnetometer observations. And they found that while the southern hemisphere of Jupiter is predominantly dipolar, the northern hemisphere is actually strongly non-dipolar. And this lopsidedness in Jupiter's magnetic field suggested that maybe instead of a solid core, Jupiter's rocky and icy core might instead be partially dissolved into its metallic hydrogen region, and that would lead to this multi-layered dynamo. So if we look at the magnetic fields of solar system planets, I think that we can immediately see that their magnetic behaviors are incredibly diverse, right? Of those planets in our own solar system, the surface average radial magnetic field strengths span 3 orders of magnitude. Some planets have topologies that are dominated by dipoles and some do not. Saturn's dipole moment is nearly aligned with its rotational axis. Earth and Jupiter are tilted by about 10 degrees. Uranus and Neptune are nearly sideways. And this is just our own solar system, right? One of who knows how many solar systems we have in the universe. So if this is the diversity of magnetic behaviors that we observe in just our own solar system, I always like to pause and just ask myself, what else could we learn from studying the magnetic behaviors of our thousands at this point of confirmed exoplanets. So right now there are 4 possible ways of probing exoplanet magnetism, and these are all in various stages of development. The first 2, I would call them indirect methods. So there's been interest for a while now in indirectly inferring magnetic fields measuring pre-transit bow shocks in hot Jupiter atmospheres. And so these bow shocks kind of occur, you can imagine, when ionized material from the host star piles up against the planet's magnetosphere. And Wilson Colley, who was a dear colleague of mine at ASU and now is here at CU, has been involved in some of this work. Wilson has also been at the leading edge, along with Evgenia Shkolnik, in inferring exoplanet magnetic field strengths by measuring the power that's emitted when the planetary magnetic field interacts with its host star magnetic field. And this basically manifests as periodically varying stellar emission lines that are synchronized with the orbital period of the planet. And so Wilson had some really nice work that's come out over the last couple of years, and I'll show you some more of it later in this talk. Okay, so for direct measurements, Antonio Oklopcic has been leading the theoretical development of harnessing the magnetic broadening and polarization measurements of helium-1083 nanometer emission in hot Jupiter atmospheres. And Jessica Spake, also a 51 Pi B fellow at Caltech, is now working on the observational arm of this effort. And I think that over the next couple of years, we'll be seeing more and more papers looking for this kind of emission using instruments like SPIRU. Okay, and then I think that we will also soon be seeing the first detections of radio-aurorae from gas giant planets. So what I'm showing you here is the first detection of Jupiter's radio-aurora. And basically what we look for are pulsing and highly circularly polarized radio emission from magnetized planets. And Burke and Franklin, this came out of work by Burke and Franklin in 1955. This inspired a decades-long search for radio-aurorae from exoplanets. And even though we don't have any confirmed detections of exoplanet aurorae yet, as you can see, there are many, many teams that have been working on this effort, and with instruments like LOFAR coming online, I think that soon we'll be seeing some of these detections. Now, for my own research, I use none of those 4 methods that I just talked about, because there are actually 5 methods of studying exoplanet magnetism. So my wavelength of choice is gigahertz radio emission, and I look to Jupiter for inspiration when I design experiments for objects that are outside of our solar system. Now, what I'm showing you here is basically Jupiter emits 2 sources of radio emission that probe its magnetosphere. It actually has 3 sources of radio emission, including thermal emission from its clouds, but for all intents and purposes, that is not detectable from the ground for extrasolar objects. And while there's been a lot of focus more recently on aurora, I personally think that we actually need to study both sources of its radio emission. And here, Jupiter has aurora, and I'm showing you its UV emission for illustration purposes, but it also produces radio emission from its radiation belts. Right? And so I think that by studying these 2 sources of radio emission together, we can learn about things like the dynamos that generate their planetary magnetic fields, their auroral behaviors, and also the conditions of their magnetospheres, including the plasma that might be trapped in them. So in my talk today, I'll be mostly focusing on these first and last questions, but I'll touch a little bit on the second question. Okay, so right now, direct observations of exoplanet magnetism, as I mentioned before, remain out of reach. And so instead, I've been using this 5th way of studying exoplanet magnetism, and that's with brown dwarfs. Now, brown dwarfs you can think of as intermediate objects between stars and planets. And brown dwarfs essentially share similar convective magnetic dynamos as gas giant planets. And so the same physics in theory is relevant for that's relevant for planetary dynamos is probably relevant for brown dwarf dynamos. And so the idea is that we can use brown dwarf magnetism, which we can already observe today with facilities that exist today, as laboratories for studying planetary magnetism and also think about what kinds of facilities we need in the future. And actually, there's research that has come out of the last couple of years that shows that brown dwarfs are magnetic analogs for gas giant planets. And so, for instance, beginning in 2015, a trio of papers came out that established that brown dwarfs can manifest aurorae like planets. And this trio included both some fantastic work that Sebastian Pineda, who is a research scientist here at CU, led, as well as my own work, which led to the first detection of an aurora on a planetary mass extrasolar object. And I'm showing you its radio aurora here. Now, brown dwarf radio aurorae are characterized similar to planetary radio aurorae by rotational modulation and strong circular polarization. And the identification of this particular component of brown dwarf radio emission as auroral in nature, rather than folks used to think it was flaring, but this is actually auroral, was actually really consequential because radio aurorae are emitted at frequencies that directly map to magnetic field strengths. And so by using aurorae to measure brown dwarf magnetic field strengths, we can then test planetary dynamo models. And so I'll give you an example here. So this is a seminal model of planetary and stellar dynamos. The thick black line comes from a suite of planetary dynamo simulations that has been scaled up to stellar parameters and also brown dwarf parameters. And essentially this scaling relationship argues that the thermal energy that's convected in these objects deep interior is ultimately what determines the energy in their magnetic fields. And then the shaded gray region shows you sort of the 3 sigma uncertainties on this model. And 2 years ago, Wilson Colley, in collaboration with Evgenia Shkolnik, showed that the extra heat that's deposited by host stars into hot Jupiter interiors. So you have these Jupiters that are really close into their stars and they're irradiated, strongly irradiated by their host stars. So they have all this extra heat. So if all that extra heat is deposited into their deep interiors, then that could account for the surprisingly strong magnetic fields that they were measuring from, in this case, star-planet magnetospheric interaction emissions. So these are indirect measurements. But the idea of just the idea that all this thermal energy being deposited into these guys' deep interiors is, was just really cool to see. And one of the things I want to point out here is that these points are sort of on this line because Wilson has already taken into account the extra heat that could be deposited by the host stars. Now, if you talk to Wilson, he will agree that that one of the caveats of the analysis here is that you have to assume that there's an ideal energy conversion efficiency, right? That all of the energy is deposited into the centers of these planets and all of it gets turned into magnetic energy. But I think we can all agree that this is unlikely to be the case, that ideal energy conversion is unlikely to actually be occurring. And actually, if we look at planetary magnetic field measurements within the context of isolated and cold brown dwarfs, we actually see a really interesting twist. Right, so these isolated brown dwarfs, they don't get a boost of extra energy from their host star because they have no host star. So we can remove the question of thermal energy from host stars. And yet, like the hot Jupiters from Wilson's study, they also have anomalously strong magnetic fields, right? So here, again, these already account for extra thermal energy from host stars. They would all be shifted over a little bit to the left. These have no extra thermal energy from a host star. And what I want you to pay attention to is just that there's just something going on here. They're more magnetized than they ought to be, according to this particular scaling relationship. And so a big question that kind of arises from this work that I led as a grad student is what else, in addition to convected energy flux, contributes to these stronger than predicted fields that we're observing both in brown dwarfs and also in hot Jupiters. So around this time that I was really wrestling with the VLA data that led to these measurements, Jonathan Gagné discovered that one of my targets was quite young and only had a mass of about 12.5 Jupiter masses, or right on the cusp of being a planetary mass object. So this particular object, SIMPA 136, is so far the first and the only planetary mass object that has been detected at radio frequencies. And when I looked at this object, when my mentor Evgenia Shkolnik looked at this object, what we saw was this very young, 250 million year old, very magnetized planetary mass object. And we wondered, does age or characteristics related to age, like excess heat, play any factor in an object's magnetism? Like, how important is thermal energy? And so for one experiment, we obtained 4 to 8 gigahertz VLA observations of another young planetary mass brown dwarf. This particular object is only 150 million years old. It is between 11 to 12 Jupiter masses. Our observation spans 16 straight hours, which is enough for an entire rotation period on this object. And our observations also were 4 times deeper than those that led to the detection of the first planetary mass object with a radio aurora. And quite possibly, I'm pretty sure this is the deepest set of radio observations on brown dwarfs ever, and probably stars, actually. So, yet if you see here, I've been pointing at an object that you cannot see, right? And that is because we detected no radio emission. And I often get a question when I don't see radio emission. People will often ask me, does this mean this object doesn't have a magnetic field, right? But naively, that we have to actually be quite careful about interpreting non-detections. And that's actually because magnetospheric radio emission requires 2 ingredients, right? We need both the magnetic fields and also the electrons that produce that radio emission. And so by itself, the lack of detectable radio emission from an individual object can't disentangle this degeneracy between the lack of strong fields or electron sources. But together, a population of brown dwarfs might be able to tell us if certain characteristics play an important role in magnetospheric conditions. And so far, the detections of radio aurorae have shown us that thermal energy seems to underpredict strong magnetic fields in brown dwarfs and potentially also gas giant exoplanets. And also that planetary mass objects can generate kilogauss magnetic fields that are over 200 times stronger than what we observe on Jupiter. But what can we conclude from non-detection? So these conclusions come from detections. And yet there's about a 5 to 10% detection rate of radio emission from brown dwarfs, right? And so that tells me that there's a whole bunch of information that exists in these non-detections. And moreover, that if we really want to make use of all these observations that we have for which we don't have detections, we really need to figure out what we can conclude from non-detections. And so this is really where the non-auroral component of magnetospheric radio emission comes in handy. So, like planets, brown dwarfs have a source of non-auroral quasi-steady quiescent radio emission. And up until now, this quiescent component of brown dwarf radio emission hasn't received as much attention as aurora. But when we're trying to understand the implications of non-detections, we can actually turn to statistical studies of this roughly steady state quiescent radio emission. And so before I jump into this next section, I wanted to take any questions. Yeah. Yeah, so the question I got was, how do I know that the flare-like radio emission that I'm seeing from brown dwarfs is actually from aurora and not from flares? It's a combination of things. So part of it is that the rotation periods match up with what with the rotation periods or spin measurements that we have of these objects. But part of it also is just flare emission in brown dwarfs and also low mass stars is generally gyrosynchrotron radio emission, and it's an incoherent emission process. And this particular radio emission that I'm observing is coherent, and the only source, the only non-extragalactic source of coherent radio emission that we know of is from this process called electron cyclotron maser emission. And that's the process that generates radio aurorae on solar system planets. Yep. Yeah, so the question is, are there any variations in the amplitude of the auroral emission? And the answer is yes. And my understanding is that the radio aurorae from solar system bodies is also quite variable, and it just depends on a lot of different conditions, like even where we are in the plasma torus of around Jupiter can contribute to how strong that emission is. And so it's no surprise that there are variations. Yep. Yep. So the question I had is, the aurora seems to be quite short-lived. They're sharp spikes. And that really just comes to, here, let me see, this is sort of a schematic diagram of an aurora. And this, basically what we have is this yellow cone is essentially, it's a cone that, it's the cone of emission of the aurora, and the actual emission is actually being emitted along the edges of this cone. And the width of that cone depends on a couple of different factors, but what we're seeing is essentially the beaming of this radio emission. So it's strongly beamed. Yeah, so this particular object that I'm showing you is extremely well studied at infrared infrared wavelengths, and so we have rotation measurements for this particular object. Yep. I'll take one more question and then I'll go on. Grief.
You said earlier that the aurora was basically having a magnetic field and what the details of the electron source.
Yeah.
So the variation in the amplitude of the aurora, that mostly just be associated with the electron source, or is there also some?
I think that's a fantastic question, and the short answer is we don't know, and I would like to know. Yeah. Okay. Oh, and for those of you on Zoom, Girish wanted to know if the amplitude of the radio emission had to do mostly with the details of the electron source or the magnetic field itself. Okay. So for those of you who have questions, hold on to them, and there'll be more opportunities for me to answer them. So let's see. Okay, so this is where I was. Okay, so as I was saying, we have aurora and we have also this quiescent emission. And what I've labeled here are radiation belts because this is the source of that emission in Jupiter. But I do want to note that there's actually a lot of debate in my field right now over the nature of the origin of this magnetospheric plasma. That's not auroral. So there's a subset of people who think it might be flares from brown dwarfs, like those that have been observed by Rishi Paudel or James Jackman with TESS. Or there's a subset of people who think that they could be extrasolar radiation belt analogs. And there are good reasons that both sets of people have. And I think one of the interesting questions of the next decade really is answering what really is this quiescent radio emission. So as I'm showing you results for this next section, please keep in mind that this is a very active field of research. It has many open questions, and I, of course, come to it with a certain lens. Okay. So the point in the story where we left off was that thermal energy seems to underpredict strong magnetic fields, and trying to search for radio emission from another nearby and very young brown dwarf didn't pan out. But what happens when we compare the radio occurrence rate of young brown dwarfs to older ones? Now, in a paper that I submitted last year with Evgenia Shkolnik, I developed and validated the first framework for calculating the occurrence rate of radio emission in brown dwarfs. And this was important to do because up until this point, we'd really only been looking at detection rates, and yet what exists in literature comes from a variety of radio telescopes of different generations, so different sensitivities. And on top of that, radio observations don't actually lend themselves well to injection tests. And so we have to find a way to account for these systematics without having to re-reduce all the data that exists out there. And so by combining literature data with a new survey of young brown dwarfs and using this new occurrence rate framework, what she and I are finding is that youth or characteristics related to youth do not actually enhance the radio occurrence rate for brown dwarfs. And so what we're seeing on the x-axis is the occurrence rate. And then this is the probability density distribution of that occurrence rate given the data that we have on hand. And what you'll observe here is just that the young objects do not appear to be more likely to be radioactive compared to the old objects. I'm not prepared to say that they are less radioactive, but I am prepared to say they are not more radioactive than old brown dwarfs of similar masses. Right? So what we now know is that the magnetic fields and the electrons that are necessary to produce this non-auroral quiescent radio emission seem to stick around for long time scales. And I would say that this result actually only underscores my previous work, showing that we need something else in addition to thermal energy to explain the strong magnetic fields that we're measuring. Because young objects, young brown dwarfs, they spend their lifetimes cooling and contracting. The older a brown dwarf is, then the cooler it will be compared to a younger object of the same mass, right? And yet younger objects are not more likely to be radioactive. Okay, so what if rotational energy contributes to the dynamo energy budget? So if that were the case, that would actually be really exciting, because right now in existing planetary dynamo simulations, such as the one that I've been showing you here, rotational contributions to the magnetic energy budget appear to become negligible for objects that are rotating at sufficient speeds. And so, in contrast to planetary dynamo models, in dynamo modeling of low mass stars that also have fully convective dynamo regions like brown dwarfs, that have been inspired by Zeeman Doppler imaging by Julien Morin and his group, magnetic fields seem to fall into two regimes. Right? Either they have strong dipole fields, the ones that are rotating more quickly, or they seem to have weaker dipole fields and stronger small scale fields for the objects that are more slowly rotating. And so one of the questions that I have is, does this behavior extend to brown dwarfs? And it might, right? Evgenia Shkolnik and I also show that about 15 to 20% of brown dwarfs have quiescent radio emission, compared to the 5% that Monte Carlo simulations from a different study suggest may have radio aurora. And so what is this telling us? Well, aurorae at gigahertz frequencies trace kilogauss magnetic fields. And so we know that all brown dwarfs with aurorae also have quiescent radio emission. And so that means that at least 5% of observed brown dwarfs have very strong magnetic fields in the kilogauss range. But what about the remaining 10 to 15%? Since quiescent emission is emitted via an emission mechanism that manifests at tens to hundreds of harmonics of the electron gyro frequency, they trace magnetic fields that are roughly 10 to 100 times weaker. And so it's possible that what we're seeing is evidence of a weakly magnetized population. And actually in 2020, Harish Vedantham's team announced the first 144 megahertz detection of a very cold brown dwarf using LOFAR. And this corresponds to 25 Gauss fields. So it's looking like rotation could potentially be one of the distinguishing factors between weakly versus strongly magnetized brown dwarfs. But this is all very preliminary and a lot of work needs to be done here. Nevertheless, in 2017, Sebastian led a team that showed that radio detection fractions increase with projected rotational velocity v sin I. And this also hints that rotation may play a role, right? And then finally, in another paper that I led in collaboration with Sebastian, we're showing that even when we account for observational effects and effective temperature, there's something about being in binary systems that enhances the quiescent radio occurrence rate. So what I'm showing you here in blue is the radio occurrence rate for binary systems that I've predicted from thousands upon thousands of randomly drawn single object samples that I've turned into binary samples with a temperature distribution that's similar to the temperature distribution of my binary sample. And we can see here that binaries, for some reason, are much more likely to emit radio emission than what their single object counterparts predict. So one hypothesis for why this might be the case is that rotation matters. And this is because binary stars are more magnetically active than their single object counterparts. And this could be due to tidal spin up that enhances their rotation rates and therefore their magnetic activity. And so one question is, could something similar be happening for brown dwarfs? Now, again, I want to stress that there are a whole bunch of other variables into what could be causing this radio occurrence rate in binary systems to be elevated. But one of the questions that's still open for investigation is, does rotation rate matter? Okay, so I would say that, from population statistics of this non-auroral component of radio emission, we're starting to draw several really interesting conclusions, which is that youth does not seem to strongly affect magnetism, and that's just another nail in the coffin that we need something else in addition to thermal energy. We're also seeing the hints of a population of weakly magnetized brown dwarfs, and I think that over the coming years, we'll be seeing more and more detections of these at low frequencies that hopefully will shed more insight into them. And then finally, we know that there's something about binarity that enhances the quiescent radio occurrence rates of these objects. And I'm not ready to say why this is the case, but I currently have a radio survey of every observable brown dwarf binary system in the Northern Hemisphere. And one of the things we'll be looking at is how that radio emission changes, how that occurrence rate changes with respect to binary separation, for instance. Okay, so for the final 10 to 15 minutes of my talk, I'll showcase what kinds of science I think that we can really look forward to in the next decade. But before we jump in, I wanted to pause and take more questions. Yep. Mm-hmm.
This question about whether the entire is layers or exoplanet platform and stuff like that. Wouldn't like you with their flow you where like the nature of this emission? Ask the question of pose and answer.
So my understanding of your question, and correct me if I'm wrong, is that I'm curious about where this quiescent radio emission is coming from, and can't I answer that just by looking at Jupiter? Yeah, okay. That's, I think, very tempting for me to do, but if there's anything that we've learned from, just discovering the first set of exoplanet systems that we ever observed, it's that our solar system is not necessarily representative of what exists elsewhere in the greater universe. And so I would say it's good to take what we see here in the solar system as inspiration, but it's important to be skeptical and think carefully about if it actually maps over well or not. And also, brown dwarfs, they form via different formation mechanisms from planets. I don't know yet if that has an impact on what we see. So I would not say that there are 100% perfectly analogous systems. So we have to be careful. Wilson? Yeah. There is no bin in this particular case. It's just every single binary system that we had radio observations for. Most of them were drawn from the literature. We do know that none of the binary systems are close enough for there to be direct magnetic interactions. So we can rule that out. And beyond that, you know, the hottest, I restrict the sample so that everything is for astronomers in M7 or M8 and later. But one of the things we have to think about is, you know, maybe there is some flaring behavior going on, and like what Sebastian has shown over the course of his work is that there's this really interesting transition that occurs in the magnetic behaviors of systems as we're going from low mass stars into brown dwarfs, and that might happen in around the early L's or 1600 degree Kelvin-ish temperature range. And that's one thing that I really want to dig into, and that's why I needed this much larger sample. So the sample I have will expand the current sample from 30 objects to over 120. Yeah. Mm-hmm. Yeah. Yeah.
The way I usually think about this,
Yeah. So that's a fantastic question. So essentially, like, does it actually make sense that a hot Jupiter that's close to its host star would have a stronger dynamo, because the convection is really the convection that seems to be one of the major driving cases for the magnetic fields of these objects. And if you have an object that's closer to its host star, won't that change the temperature gradient of that star and therefore its convection? And I think that's actually a fantastic question, and it's one of the things that I am also skeptical about. And that the particular paper, theory paper that came out with this, I don't actually think looked at that particular question. It was just looking at the thermal energy budget period, and I think it's a question that needs to be looked at. So I am also unconvinced that basically, I agree with you that I am skeptical that it's as simple of a matter as just that thermal energy. Yeah. Mm-hmm. One more question and then I'll keep going. Yep. Yeah, that's another question, and that I have. So the question is, does the stellar wind of the binary companion have anything to do with the strength of the emission? That is a fantastic question, and that's why I constructed my upcoming radio sample to be able to look at different ranges of separation of binary separations. That's one way of getting into it. But I also, one of the challenges is that it's not clear how strong of a wind some of the lower temperature systems will have, especially brown dwarf binary systems. And so, we don't know yet. Okay. What is the time, the colloquium ending time, so I can make sure? Okay, perfect. Okay, perfect. That is exactly perfectly timed. Okay, so for those of you who are grad students in this room, you can look forward to your postdoc years, which are both years of tremendous freedom and also existential anxiety. As we think about where our careers will go. For those of you who are postdocs, we're down there in the trenches and I understand you very well. And those of you who are faculty, you probably think fondly back on your postdoc years. And also thank you to those of you who served on the decadal committee, especially because I was very pleased with some of the decadal recommendations. But as an early career postdoc, the future is something that's very much on my mind all the time. And so back in 2020, Sebastian and I co-led a decadal white paper that I encourage all of you to check out in addition to reading the newly published decadal survey. And in that paper, we lay out several questions that we think will be really the questions we'll be able to start answering in this next decade. And so the first one that I'm extremely interested in is what are brown dwarf magnetic topologies? Okay, so the last time that I showed you this plot, we had concluded that convected energy flux can't predict strong substellar magnetic fields. Right, but there is actually a subtlety to the dynamo model that I'm showing you here. And it's that the models only apply for objects that have magnetic fields that are dominated by dipoles, right? And so given this, the fact that I'm seeing this departure between the data that I measured and the model here raises a really interesting question. Do these brown dwarfs have magnetic topologies that are not dominated by dipoles, right? And there's actually a fair amount of debate in my field about the topologies of these aurorally emitting brown dwarfs. So in 2015, Christine Lynch modeled the radio aurora from the M9 dwarf TVLM 513. So these are the observations of it. We have frequency and then rotational phase. And these are her models. And what she's showing is that dipole fields can't reproduce the observed dynamic spectrum. And instead, coronal loops of about 1 to 3 stellar radii are better able to reproduce her observations. And actually, one of the limitations of radio aurorae has been that it doesn't actually contain topological information about magnetic fields. And this is because the aurora are emitted at the local cyclotron frequency. And so in other words, it tells us nothing about the global magnetic field. And so further out in the magnetosphere, emitting electrons will radiate at a lower frequency where the magnetic field is weaker, and closer to the surface of the object where the field is stronger, it'll emit at a higher frequency, right? And this is why we have this broadband emission because these electrons are spanning multiple magnetic field strengths. And we don't actually even know that they're radio aurorae trace dipole fields. So a couple of years ago, I discovered some really cool work by Nick Schneider's group. So Mars does not have a global dipole magnetic field, and yet we know now that it can emit aurora thanks to Nick Schneider's group. So, what we're seeing here on the left is a laboratory model of an aurora on Mars in which a miniature sphere is magnetized to simulate a magnetic field. It's then put inside a vacuum chamber filled with carbon dioxide to simulate Mars's atmosphere. And then it's really cool. People shoot electrons at it to see how the magnetic field, the electrons, and the surrounding atmosphere interact. And then on the right is a video of Mars's sort of whole planet aurora observed using the imaging ultraviolet spectrograph of MAVEN in 2017. And this is just one of 3 different types of Martian aurora. There's a second one that Nick was telling me about today that is more localized and corresponds more closely with the crustal, the locations of the crustal magnetic fields. And we know pretty much nothing about the radio behavior of Mars, right? So one of the things I look forward to seeing one day is radio observations of Mars. Now, we can start getting into the question of magnetic topologies by imaging the magnetospheres of brown dwarfs. So I think that a next generation very large array, which got a lot of nods in the decadal survey, will actually play a really pivotal role in answering this question. So this instrument will basically have 220 radio dishes that span the entire, from Hawaii all the way across the United States. And what that allows us to do is basically start resolving magnetospheres. So this is an example using the very long baseline array, which is just an array of, I want to say 9 dishes, but I actually can't remember off the top of my head right now. But this is UV SETI B, and in 1998, Arnold Benz was able to resolve a post-flare corona. And what we see here is basically the flare being captured by its dipole magnetic field, or what was interpreted as its dipole magnetic field. And then more recent observations by Jackie Villadsen using an upgraded very long baseline array is starting to give us insight into the magnetic polarity structure, right? Circularly polarized, left circularly polarized of the same star. right, so what I would like to do is do this for brown dwarfs. And basically, if their magnetospheres are filled with plasma, which is what I hypothesize may be that quiescent radio emission, then we could potentially resolve out these magnetospheres. And if we're able to resolve them out, that'll tell us that there's a very strong dipole component. So a next generation, very large array with very long baseline interferometry capabilities like this could do something like that for brown dwarfs. Okay, so the next question that I think will be a focus for this decade is, what are the characteristics of exo-aurorae? Okay, so thanks to VLA and Spitzer, we're already actually breaking ground into investigating these multi-wavelength characteristics. And in actually the work that I led in 2016, some of my detections suggested that some of the coldest brown dwarfs may have aurora that also manifests as infrared photometric variability. And you can sort of imagine that the upper atmospheres are getting heated at infrared wavelengths, and then you have this auroral oval kind of rotating in and out of view. But in recent work that my graduate student, Tyler Ritchie-Yowell, just published, we show that 3 and 4 micron variability as well as J-band variability are not in fact good tracers for the aurora on the coldest brown dwarfs. And so, you know, Tyler was an extraordinarily good sport about all of these non-detections. But she was very excited when we did find one aurora. So in an initial sample of 17 brown dwarfs with infrared variability, Tyler detected just one object. And we measured an occurrence rate of aurora that's indistinguishable from a random sample of brown dwarfs. But instead, it appears that a stronger tracer of auroral radio phenomena is H-alpha emission. And this supports work that Sebastian led in 2017. He showed that there's this really lovely relationship between the flux density of radio luminosities and H-alpha luminosities. And our object that we detected with Tyler plops right onto this relationship. Okay. So, you know, what is the spectral signature of exo-aurorae? I think that simultaneous multi-wavelength observations of aurorae using the next generation VLA, or even the VLA right now, and other facilities that will come online soon, like JWST and its successors, or ELTs, will be absolutely essential for characterizing and building the first models of exo-aurorae so that we can learn more about their physics. And this particular branch of investigation is something that Sebastian's very interested in investigating. So I encourage all of you to also talk to him about this effort. So along these lines, I do want to mention that he and I and Johanna Voss have a proof of concept experiment right now with Hubble Space Telescope and Very Large Array simultaneous observations. So just keep your eye out in the next year or two for a publication that will come from that. Okay, so finally, do brown dwarf satellites power their aurorae? So the reason why I think this question is so important is that in addition to telling us about brown dwarf magnetism, brown dwarf radio aurora could also could give us clues not just about the brown dwarfs themselves, but about potentially the nature of exomoon analogs. And so in this way, we could use brown dwarfs both as analogs to study gas giant planets and also sources to actually study terrestrial type objects. So when most people think about aurora on planets, what they picture is the solar wind or solar flares interacting with the planetary magnetic field, like what we see in this picture. But there are actually 2 other important sources of aurora in our solar system, which both involve interacting with planet satellites. So number 1 is that Io's volcanic activity populates this dense plasma, torus of plasma around Jupiter. And then that plasma torus interacts with Jupiter's magnetic field here where that plasma torus stops co-rotating with Jupiter. So this is not the sun, this is the artist's interpretation of where that plasma torus stops co-rotating with Jupiter. And that basically drives a current into the Jovian atmosphere and produces the oval that you see here, the auroral oval that you see here. So in addition to this, to this source of aurora, there's actually a second one where Io's ionosphere directly interacts with the Jovian magnetic field. And that drives a second component of the aurora, which are these bright spots and streaks that follow the magnetic L shell of Io's orbit. And so the aurora on isolated brown dwarfs can't be from a solar wind because they're isolated, right? And so this suggests that their radio aurora might instead point to the presence of exomoon analogs or exoplanets around them. And there's theory that suggests that thinks that there very much is likely to be planets around brown dwarfs. And so if this is the case, then satellite-driven aurorae could tell us about the natures of the satellites themselves, right? The strength of the auroral emission depends on things like the size of the ionosphere or the magnetosphere. The auroral satellite interactions, they have these uniquely characteristic arcs. And those arcs depend on things like orbits, rotation, magnetic fields of satellites. And so right now there are models that are being developed for future detections of exoplanet radio emission, but I think we should develop them for brown dwarfs right now. And adapting these models to brown dwarfs together with investing in something like the next generation VLA, which could give us the kinds of exquisitely detailed observations that we need to see this kind of detail, could potentially yield really cool insights into exoplanet magnetism, and in particular exoplanets around brown dwarfs. Okay, so this is really only the tip of the iceberg. And just to conclude, to really be able to build on the cool results that I've shown you from my work and the newness of this field, we really need to be investing in multiple radio instruments across the frequency spectrum. So for brown dwarfs, we need to be looking at hundreds of gigahertz, including the NGVLA and the deep synoptic array. For gas giant planets, we want to be looking at the hundreds of megahertz. So LOFAR, for instance, or the Owens Valley low frequency array, long wavelength array. And then for terrestrial planets, we'll have to go into space above the ionospheric cutoff. And so CU Boulder, together with Caltech, are leading one such initiative to be able to hopefully build a dipole array on the dark side of the moon. And if that happens, I think we could get some extraordinary data from that. And so with that, I'm happy to go back to my conclusions and take any remaining questions.
Thanks, Melodie. You're doing a good job running Q&A yourself.
Yeah.
So I'll let you continue
Thank
to
you.
do that with two caveats. One, you raise his hand and then give a high sign.
Okay.
At some time. Maybe 5 or 6 minutes.
Yeah.
Hearing you on Zoom, so when you said enter your name thing in the chat, you might let us say repeat that statement. Say it, have a question. Please say it.
Oh, okay.
Just say it out loud.
Oh, if you have a question in Zoom land, please type it in the chat.
Sure. Okay. And we've had a lot of Q&A so far, so that's been great. So
Yeah.
Go ahead, take it away.
Yep. So the question that's being asked is, are there any insights about the plasma properties from H alpha? To be honest, that question is entirely out of my depth, and I would love to dig into it and tell you more once I dig into it. So. Yep.
I have a question that might be down at the weeds. When you were talking about the different frequencies that happen from electrons in different parts of their starting to wonder the time series observations as signal that radio should be beamed. And so as you intersect that cone at different places, you're going to expect different frequencies. Use that as signals.
I mean, yes, and I would love to do that, but you need to know basically the orientation of that field on the sky, right? The orientation of like the magnetic field with respect to the spin axis of the object. And so there's just so much that we don't know right now that one day I would like to do that, but I don't think we have enough information to do that right now. But like one of the projects that I sort of have going for the last couple of years is trying to back out the magnetic topology of an object. I mentioned it to you in one of our one-on-one meetings, and from the same project, I might, if the data is good enough, I might be able to figure out the orientation of its magnetic field with respect to its spin axis. And if that's the case, then that would sort of be the first time that we could actually back out some of this information. Yeah. Yep, Nick.
One of the, you make a good point about thinking from our solar system. And one of the weird lessons of the giant planets is they all have magnetic fields, but not for the same reasons. Whether weird for Neptune or hydrogen. Does it get simpler when you get to brown dwarfs, or are there still mysteries of how the field is generated?
I would say, we're right now, I would call it simple, but only because we don't know very much. And so actually one of the questions I've had is whether or not this is showing instead a brown dwarf relation that sort of is distinct from planetary magnetic fields, and if so, why? Another question that we have is, I've been referring to brown dwarfs as planetary mass or not planetary mass, but it's unclear to me that the mass of the object actually matters, and maybe what matters more is the formation mechanism of it, because some brown dwarfs, Mart has been showing that some brown dwarfs may form by core collapse and some may form by core accretion. And if that's the case, then some brown dwarfs may have solid or partially solid cores and others may not, and that could also influence their dynamos. And so the short answer is that I expect it to be far more complicated than what I've been showing you.
Thank you.
Yeah. Yeah. Oh man. So the question is there any hope of doing radio velocity measurements on some of these brown dwarfs that I have radio measurements for, to try to back out if there is an exoplanet around one of them? I would love to do that. Phil Muirhead and his student Patrick Tamburo at BU have been working on this effort. I gave them the list of all of the radio brown dwarfs that exist, and they were the first ones that they looked at. They haven't seen anything yet, but also just it's incredibly challenging to make that observation because we're looking at terrestrial planets around very, very, very faint objects. And so it's not even clear to me that they have the sensitivity to do that. Yeah. But when we do get that sensitivity, these objects, in my opinion, are the first ones to look at.
Yeah. Can I do one last question? Here we go. So on a plot like this, I've been thinking about this. A whole hour.
It's fine.
Really just eight orders of magnitude
Yeah.
axis, and I have an instinctive distrust of expecting any trend to last that many decades on an axis. And so I was trying to figure out if this is really more of a heuristic plot to see how much we deviate from that when we get off into the boonies, or if people have a reasonable expectation that this should hold.
I would say both. So I would say that we know that to a certain degree, thermal convection matters. It's just the question of, is it the only thing that matters for things that are rotating fast enough or have dipole fields? It's not clear to me that it makes sense to say that it is the only thing that matters. So now the question is, okay, based on how much it's deviating, what kind of physics can we get out of that? And I'm talking to Dave Stevenson, who's been working in dynamo theory for a long time. He thinks that like rotation may matter, and even just talking to Rakesh Yadav, the simulations that led to this particular relationship, we're just limited by computational resolution. And when you're getting to faster and faster rotation periods, or objects like brown dwarfs that have a very sharp density profile, the smaller scales matter more and more, and maybe that's also partially why we're seeing this disagreement. So there's a real need for just better computational models, but also trying to understand what else in addition to what we're seeing goes on. So it's both a heuristic thing and also, there's some amount of the baseline physics of it is unlikely to be completely overturned. And one thing, I'm interested in talking to Ben Brown here, partly because I just want to talk to him about adapting some of his models to Brown dwarf parameters.
Yeah, thanks. So let's stop there, and you can put questions up front if you have them after, but let's thank Melodie one more time. Hooray for in-person colloquium.